Chapter 4 is about alkanes. So alkanes are hydrocarbons. Hydrocarbons are compounds made only of carbon and hydrogen. So these are common in petroleum, pheromones, and other places in the natural world. These are non-polar compounds. They have no significant dipoles. There's a tiny dipole between carbon and hydrogen, but a lot of these cancel out. So hydrocarbons are considered non-polar. You see oils that come to the top of chicken soup. Oil and water don't mix. Water's polar and hydrocarbons are not. And I think you've learned that in general chemistry. In any case, these are non-polar compounds. Alkanes are hydrocarbons with no pi bonds. That is, they're saturated. Compounds with pi bonds are called unsaturated. And alkanes have no cycles. All of the carbons on alkanes are sp3, so the bond angles are 109.5 degrees. And different alkane compounds have different numbers of carbons. So we're going to talk about linear alkanes in this particular presentation, and that's a form of alkanes. We're also going to talk about branched, so let me explain both of these. Linear alkanes have one or many CH2s that are connected together. And at the ends of this chain, there are CH3s, and this is so that every carbon has 4 bonds. So the example that's shown is CH3, CH2X. X can be any number, a whole number, for example, and 0, 1, 2, 3. And the common molecular formula is CnH2n plus 2, where n is the number of carbons that the molecule has. And this should make sense to you because you have a bunch of CH2s connected together, even at the ends, but then the ends are capped with 1 hydrogen each. So you have CH3s as shown up above, so it's 2n plus 2. So linear alkanes are compounds where you have a line of carbons essentially, and this is how we define linear alkanes. Branched alkanes have one or more of the CH2s in the middle of the chain where the hydrogen gets replaced by a carbon. And so we'll give examples of those. Here's an example. One of the middle carbons, one of the hydrogens is replaced by CH3. The molecular formula for this is also CnH2n plus 2, like it was for linear alkanes up above. And I want you to consider the following. We've taken off 1 hydrogen, but we put in a CH3. Essentially what we've done is added a CH2 to this compound. Because the hydrogen we took off of one of the carbon in the chain, that one we put on the end carbon. So this is also CnH2n plus 2. And another example of this we're showing here on the right. Here we have multiple branching for these compounds. We have a CH3 group on the left. We have a CH2CH3 group. Below, we have a CH with 2 CH3 groups above. We're going to talk about the names of all of these, but for now, you just need to know this is branched. Also, you should recognize that the more branching a compound has, the lower it's going to be, its boiling point is going to be compared to a linear compound. So if the compound below, let's say, had 15 carbons, and the branched one on the bottom right, I'm not sure how many it has, but let's say it has 15 carbons, compared to a linear alkane with 15 carbons, this is going to have a lower boiling point for reasons we'll talk about later. Let's talk about naming alkanes, but before doing that, I want to mention that if we didn't name alkanes, we'd have a really hard way of communicating with each other about chemistry. And actually, in the early days, every new compound that was discovered was given a different name with no systematic way to do this. So you had to memorize the names of a whole bunch of compounds. We don't have to do that anymore because IUPAC, the International Union of Pure and Applied Chemistry, developed a system for naming compounds. And that system is something like this. We're going to name them by this pattern. We're going to name the substituents first. Substituents are whatever is connected to the longest chain. Then we're going to name the longest chain. Then we're going to give this a surname, which is going to tell us about what other kinds of atom groups are on this molecule besides the carbon. If it's only carbon, we'll give it one surname. If it has an OH, we'll give it another surname. If it has an NH2, we'll give it another surname. But we're going to give these surnames depending on the group of atoms that give the molecule its characteristic chemical and physical behavior. So by chemical behavior, how it reacts, and physical behavior, boiling points, melting points, this kind of thing. So when we name a compound, actually the first thing we're going to do is identify the longest chain of carbons in the molecule. And if two carbons are the same length, we're going to use the one with more substituents. That means more groups that are connected to the longest chain. We're going to identify the substituents. These are a group of atoms attached to the longest chain. Some of these are going to be only carbon and hydrogen, CH3 for example. Some of them might be other kinds of atoms, OH, NH2, NO2 for hydroxy, amino, and nitro, but we're going to name substituents. Then we're going to give it a surname based on the, essentially that's going to be based on the family of compounds it belongs to, and that's related to what groups of atoms are connected to the longest chain, OHs, carbon-carbon double bonds, carbon-carbon single bonds. Some compounds have common names, and chemistry majors should know these, but we're not going to require the common names for anybody else. And so the compound below, acetone, is two CH3s connected to a carbonyl. Nobody ever calls this 2-propanone. It is called acetone by everybody, even though the IUPAC name is 2-propanone. So by the way, one of the things about naming is that once we understand the pattern, it's pretty easy to give good guesses as to what the names are for the compounds. And we'll see a little bit of that as we name compounds later on. So alkanes are made up of only carbon and hydrogen, and there are only single bonds in these molecules, and there are no cycles. Linear alkanes are made up of, if connected CH2s, a long chain, and these are capped by hydrogens. I formulated this a little bit differently last time. I said we're capped by CH3s, but here I want to remind you we're capped by two H's. We're adding two additional H's to the two NH's that occur when you have N carbons. And so this is how you get CnH2n plus 2. So there are many ways to draw linear alkanes, and those I'm going to show below. The compounds here are all nonanes, nonane compounds. N-nonane means normal nonane. Nonane is good enough. These are 9 carbons long. So the first structure I have is the structure with all the carbons and hydrogens. Then I have a zigzag structure. Then I have a zigzag structure that is folded. Essentially, we rotated some bonds around to get from one to the other. Same thing with the last one. Those are bond rotations. Bond rotations are going to be important in this chapter, but I want you to recognize all of these things mean the same thing. Pentane is another example of an alkane, a linear alkane. This is also the zigzag representation. This is C5H12 when you count it up. I got to 12 quickly because 5 times 2 plus 2 is 12. But I want to mention that just because you're C5H12 doesn't mean you're a pentane. There are other ways to connect the carbons together that don't give you the same thing as pentane. So C5H12 can be pentane, but it doesn't have to be. Branched alkanes. Again, these have a carbon connected to one of the interior carbons, and here are some examples of that. These are all equivalent representations. They mean exactly the same thing. You can draw them. In these ways. I typically prefer to draw the middle one, where I draw the longest chain in a zigzag, and then put the substituents on the longest chain. I don't fold around the carbons. I don't rotate bonds to get to the last structure on the right. So this is another example of a carbon that's branched, an alkane that's branched. And so we talked about this same one on the last slide, but these are branched. And again, this is CnH2n plus 2. This works for these as well. Linear alkanes have names depending on how many carbons are in the chain. So if the chain is, we don't call the CH4 a chain of carbons, that's one carbon. Ethane we could call a chain of 2, but there's no way to draw. We could draw a line segment that would be ethane, but nobody ever draws it that way. Everybody draws it like this. Yeah, we didn't. If you drew a line segment, you don't know whether that's a minus charge or whether that's just an erroneous mark placed someplace. So we just draw the ethane the way that's shown. Propane, we can draw the wedge for propane. That's 3 carbons. 4 carbons is butane. 5 carbons is pentane. Those names, N-pentane, N-butane, N-hexane, etc. The N comes from that. The N indicates it's a linear chain. If it's something other than a linear chain, like the compounds at the right, they have some other name other than N-butane, for example. Butane has one other isomer, An isomer is a compound with the same molecular formula, but the atoms are differently connected. And so the longest chain for that compound is 3 in this particular case, with a substituent of 1 carbon. Pentane has 2 isomers, and hexane has 3 isomers, and we go from there, building up all the possible products. So these are not all of the hexane isomers. There are going to be more. There are so many more that I just stopped drawing them. So isomers have the same molecular formula but different connectivity, and there are many more isomers in everything from hexane down. There's more isomers. And I want you to memorize the names of the linear alkanes up to dodecane. That's 12 carbons. So commit these to memory. The branched isomers, don't worry about those. We'll learn how to name those shortly, but we're not going to worry about those for now. What are the uses of the alkanes? Well, you recognize methane up above as a greenhouse gas, so we're very worried about that one in terms of the future of the environment. Stoves and heaters, they use ethane, propane, butane. These are gases. Butane can be a liquid at room temperature when it's in a cigarette lighter, for example. And the higher ones, the ones with more carbons, pentane, hexane, etc., those are in fuels such as automobile fuels. You'll recognize octane, the gas delivery device. When you go to the gas stations, it has a percent octane. That means that that fuel burns as though it's 80% octane, for example. And the higher ones, so there's fuel in there. There's also diesel in there. The ones that have even lower, have more carbons. They're not as volatile. They have a higher boiling point, and we'll talk about that later. But diesel is in there. So are thick oils and greases. Petroleum is a degraded biotissue, and so there's also nitrogen and sulfur present in these, and the combustion contributes to atmospheric nitrogen oxides and sulfuric acid. You may have heard of acid rain. That's partly because of both of these. So some other properties of alkanes really quickly. Alkanes have no polar groups, as I've mentioned before, and so therefore the boiling points are very low compared to groups with dipoles in them. If you have longer chains, you get a higher boiling point, for reasons we'll talk about shortly. And if you have more branching, you're going to have a lower boiling point. And if you have, let's see, if you're spherical, the melting points also for spherical compounds. Those melting points are going to be higher rather than lower. And again, we'll talk about those in a different presentation. So summary of alkanes. Alkanes are hydrocarbons made up of all single bonded carbon-carbon and carbon hydrogens. There are no cycles, no multiple bonds. And linear alkanes, these have connected CH2s capped by CH3s, and so they have the formula CnH2n plus 2. And the names are based on the number of carbons, and so you need to know the first 12. Branched alkanes are also CnH2n plus 2 as far as the ratio of carbons to hydrogens. And so this is where carbons are connected to some of the interior carbons. When we name the alkanes above, we name the linear ones, and we just memorize those. Here, we're going to learn how to name compounds based on the IUPAC nomenclature, and so we don't have to memorize these. And there are a lot of uses for these, mainly for the combustion is the main use for hydrocarbons, but that creates greenhouse gases, which is problematic. And so I encourage you to download ChemDraw onto your computers and to begin using it. You can practice drawing structures. You can practice naming them and asking ChemDraw for what the name is, and it'll give you a name.